In this video, we start off trig functions by having a look at the basic Sine graph. In the chapter on functions, you learned that any equation represents the relationship between, in this case, the x and the y values. And when the ordered pairs of a specific equation are plotted on the system of axes, it will form a specific graph. In the chapter on trigonometry, we saw that each trig function, along with a specific angle, gives us a unique ratio. And if we now go and plot the angles on the x-axis and the ratios on the y-axis, you will see that each trig function, sin, cos, and tan, form a unique graph. But other than with our algebraic functions, trig functions will have an x-axis that is divided into degrees. The reason for this, it represents the angle, which is measured in degrees. To determine the form of each of these trig functions graphs, we need enough coordinates that we can plot. And for this, we're going to start off with the sin function. Just like with all the algebraic functions, each trig function has a mother graph, and then there are different transformations that can happen. In our equation here, that is a, b, c, and d. We are going to start off with the mother graph, which is y is equal to sin x, and later on have a look at all the different transformations. Even though up to now we've only worked with angles up to a size of 90 degrees, there can also be angles bigger than 90 and even negative, and this you will do in more depth in grade 11. To determine the form of this graph, we are going to go up to 360 degrees. For the x values, I used intervals of 30 degrees, and now I'm going to determine the ratio or the y value that goes with every specific x value or angle size using my calculator. So starting off, my first ratio is sin of 0 degrees, and that is 0. Next we have sin of 30 degrees, which is a half or 0,5. Sin of 60 degrees will be easier to indicate on the system of axes if it's in a decimal form. This can be rounded to 0,87. Next we have sin of 90 degrees, and that gives us a ratio of 1, and now we can keep going like this. And now, just like with all other graphs, the pair of values for x and y form one coordinate. Next up we have 30 degrees and a half or 0,5, and then we need to plot 60 degrees at 0,87. And now we can continue like this, plotting each coordinate pair on our system of axes. And now you can start seeing the pattern. We already know that this is not a straight line, so when connecting these dots, we are going to do it freehand. And as you do that, you will form the pattern for the sin graph. The sin graph clearly forms a wave. And this wave is repeated in the positive direction after 360 degrees and also in the negative direction. Let's now go and have a look at the important points or coordinates on a sin graph. Just like with any other graph, it is always important to indicate the x and y intercepts. So for the mother graph, y is equal to sin x, you can remember that the y-intercept and one of the x-intercepts is at 0, 0, or the origin. Then 180 degrees later, there's another x-intercept, and again at 360 degrees. And then to form the curve or the wave, this graph, just like a parabola, has turning points, where the graph changes from an increasing or positive gradient to decreasing. The first turning point is at 90 degrees, and here we have the maximum value for the graph at y is 1. The next turning point is exactly in the middle of the two x-intercepts, and that is at 270 degrees. At this turning point, the graph changes from decreasing to increasing, and here we have the minimum value for the graph at -1. Next up, we have two new terms for trig functions. The first one is the period of the graph, and then we also have the amplitude. The period of a graph is the number of degrees that is needed to complete one full wavelength. And we've already seen that the Sine graph takes 360 degrees to complete one wavelength, and then it starts to repeat again. So the period of the mother Sine graph is 360 degrees. The amplitude of a graph is the maximum displacement from the resting position. In our graph's case, the resting position is the x-axis. And from here, the maximum displacement is either 1 unit up or 1 unit down. So the amplitude is 1. Another way to determine the amplitude is to take half of the distance between the maximum and minimum values. So in our graph's case, that will be half of the distance between 1 and -1, which is 2, and that is how we get our amplitude of 1. Because the Sine graph is cyclical and can be repeated over and over, the domain of the graph is x can be all real values. But if we focus only on the given sketch, our domain will be all x values starting at 0 degrees all the way through to 360 degrees. This can be written as x will be all the values in between and including 0 and 360 degrees, or we can write it as x is an element of the values from 0 to 360 degrees. For the range, we read from bottom to top on our y-axis. So here we will start at a minimum of -1 and go all the way up to a maximum of 1. So the y values lie between -1 and 1. In the next video, we're going to have a look at the mother graphs of y is equal to cos x and y is equal to tan x.